and giving us a talk. Okay, apparently I need to speak louder for Caulfield, so I'm going to take the mic away for Clayton and speak louder. So, Sebastian, thank you for coming. Sebastian is an associate professor at Georgia Tech. He's the associate director of the Machine Learning Center, also at Georgia Tech. He's worked in math optimization, machine learning, and plenty of other things. I'm not going to go overboard with the description. The bio is in the email. There's going to be a talk on Friday, a technical talk on convex optimization for machine learning in the machine learning seminar in Clayton. If you want the info, it's been disseminated through the machine learning mailing list. If you want the email, just ask me and I'll forward it to you. And now Sebastian will tell us about the AI God. Thank you, Sebastian.
Thank you very much, and thank you for the very kind introduction. I'm very happy to be here today. And what I really would like to do is to talk a bit about machine learning and AI and about recent high-profile failures of the systems and potential security issues and concerns that one might want to think about. So, yeah, I mean, we have seen a tremendous, 1 second, I think I'm out of cable.
The clip is still on your, yeah.
Oh, this is the mic, okay, good. Let me... Okay, good. So what we have seen over the last few years is a significant progress in machine learning and AI. The results have been truly spectacular, and that brought us to a point where we really think of algorithms and AI and machine learning to be able to solve many, many problems for us. And in some sense, we started to blindly trust these algorithms. And there's a very nice quote of a colleague of mine, I'm paraphrasing here to keep it compact, that basically says that if somebody is talking about machine learning and AI and replace the word AI by God and the meaning of the sentence doesn't change, then you really have a problem. And this is what this talk is going to be about today. But I think first let's understand where all this trust in these systems really comes from. So we have seen spectacular successes in machine learning over the last few years. For example, autonomous vehicles are very close to large-scale use and deployment. The technology, except for some very severe accidents I'm going to talk about later, is pretty mature at this point. And that's really largely due to machine learning and computer vision that is enabled by machine learning. Similarly, we have seen a tremendous and very astonishing breakthroughs in reinforcement learning, where a few years back, AlphaGo, DeepMind's AlphaGo, was able to beat the world champion at playing Go. And that was really something that was considered to be one of the high-profile AI tasks. And if you would have talked to people at that time, they would have told you that they believed that this was outside of the realm of current technology. And that was really a spectacular success for machine learning and AI, and provides some form of evidence that we are on the path of understanding how to form systems that can strategize and have some form of, let's say, general intelligence. So these two examples were, of course, more from the planning and the strategy space, something that you would consider to be in the domain of a computational task. But then, of course, there's always these things that we think that are uniquely human, like creativity and so on and so forth. And even in this space, we have seen significant progress in machine learning and computational creativity. And just to give you a bit of an idea, to give you an idea where this trust in this system really comes from, this is an example of an image that's taken in Tübingen. You see it's a lake and houses, and what people were able to do is they were they were successful in training a machine learning system to build such a system that can redraw the pictures in styles of various artists. So for example, they could redraw the same picture in the style of Vincent van Gogh, here in the style of Picasso, and then here in the style of Kandinsky. And if you look at it, it's actually pretty convincing in the way of how the system does this, and that really raises the question, which of these skills that we typically consider truly human are actually limited or truly uniquely human skills, and which ones can be replicated by a computer. And that's really what, all these examples were a part of what got people excited about AI. And if you now look at the news, the basic reasoning is that AI is going to solve it anyways. Just take the problem, build the right setup, and the problem is solved. And then there's things like people using machine learning to characterize ramen shops, then crime prediction with AI. And it doesn't really matter if you open the news, there's always something spectacular new going on every day in terms of what machine learning can do. There's crazy salaries paid for people working in machine learning. China's using it to grow roaches. and it's used in finance and many, many other things. And that really leads to us having this notion of trusting these algorithms, but at the same time, they're actually very fallible. And if you think of building these systems and using these systems, I think I like the following quote quite a bit, actually, which says that before you attempt to beat the odds, make sure that you can survive the odds beating you. And let's look at a couple of high-profile failures. So probably the most prominent ones from the recent time is the Uber accident in Arizona, where a person was run over by an autonomous vehicle. And there was a lot of speculation until, I think, 2 days ago what actually happened. There were speculations that safety features had been disabled. On top of that, if you look at the video, the driver was the safety driver was actually playing with the phone at the same time, which was probably also not very helpful. Then there were questions about whether they had enough sensors. They talked to some backup drivers that said that they saw this coming, and so on and so forth. So everybody obviously had an opinion about what happened. But I think the most critical thing that really happened, and that really became only clear 2 days ago, is that it was actually a statistical problem in some sense. Namely, what has happened is that the system was calibrated in a way to be less sensitive to false positives like plastic bags on the street and so on and so forth. But as a function of that calibration, it was also less sensitive to true positives. And it actually recognized the person but did not stop. That's actually the worst case scenario. If the scenario would have been they didn't see the person, you could have said that there was a hardware problem, but it was actually a software problem in the way of how the engineer implemented the system to deal with the people, which is maybe something that is also important from an educational perspective in terms of what we teach our students, how to deal with false positives, false negatives, and so on and so forth. So this is probably one of the most spectacular and very sad recent cases of failures of these systems. But there's many, many more failures. For example, AI being used to automate experiments in terms of how you react to advertisements. Google releasing software that is then has imbalanced training sets and suddenly detecting black people, labeling them as gorillas. Amazon using machine learning to decide where to deliver and not to deliver, which led to problems in Boston because certain areas were not really served anymore. Predictive policing that is actually creating more crime than it's solving, and many, many more issues. And yeah, so this is just a couple of examples of fairness and privacy, but it also goes into the ethics space. So for example, now certain entities are looking at predicting crime using machine learning. Now the problem with this is if you use something like machine learning or any other technology for that matter to predict crime and you act based on the prediction that you make, you will not know whether you were correct or not. So that creates a lot of issues and biases in the system. So if you would, for example, preemptively put somebody into jail, just to simplify things here, you don't know whether the person would have committed a crime or not, right? And that creates significant issues down the road. And then there's, of course, other failures where Amazon uses machine learning and all types of algorithms to assess worker performance in warehouses, and then you have suddenly reports that workers skip their bathroom breaks because they don't want to lose their job, which was in the news, I think, 2 or 3 weeks ago. And then, of course, then I don't want to talk about this. Then, at the end of the day, there's also the question of how you deal with machine learning in the context of military applications and ethics and other challenges that come with this. So, all in all, if you really think about this, we have built a technology that is extremely powerful and that we have used for many, many things. And we are at a point that the technology that we created actually is now dominating our lives to a significant extent. And maybe let's look at what this really means. Like, if you talk to people, a lot of people are really concerned about the so-called Terminator scenario, that there's this bad AI and it's going to kill us all. I think the problems actually start much earlier. And one of the examples is workforce impact. If you look at what has been happening, this is a graph for the US. I'm sure the similar graph you will find for almost any other country. Then you will see that productivity and employment typically tends to develop at roughly the same rate. And then there's this point, this great decoupling, where suddenly automation technology works so well that productivity goes up, but employment essentially becomes flat. And if you look at the statistics, you will see that every industrial robot that we deploy roughly destroys or removes 6 human jobs from the system. And if you now extrapolate this down the road, the question is, what do you do with all these people that suddenly lose their jobs? You might not be able to retrain them for various reasons, and you have to have some strategy in place. And I don't want to suggest what the right strategy could be, but I think it's a very important thing to think about the consequences of the technologies that we are developing and deploying. And just to give you an example, and I don't want to look through the whole video, I don't know who of you has ever seen how an industrial robot is programmed in the old days. So it's typically a very involved task because you have to make sure that you get all the instructions right, and everything is extremely say to the point, and it's a very detailed and complicated task to get it right. And if you look how it's done today, so this is an example from KUKA. They built a robot that you can essentially teach what to do as a task by showing the robot how the task is done. So let's have a look at how this works. So you have this robot arm, and you essentially guide the arm to the positions, show the arm what has to be done, and you have some markers on the way. And you demonstrate the task once, here in this case moving a bolt around. And let me just speed this up a bit. So you do the whole process once, and then afterwards the robot can essentially execute the task itself. So you cut something down that was taking weeks or months to develop into perfection to something that you can do in a few minutes. And that is really where the economies of scale come in, and where it becomes so easy to build these robots that in factories can automate a lot of things. And that now you can argue, well, that's all fair and square. That is in the manufacturing space, and of course you want economies of scale in the manufacturing space. But what you will see is the same thing also applies to extremely high-end or highly skilled tasks. And one of the examples here is Google's Cloud Auto ML, which is a platform where I simplify things here, but essentially you upload your data set. This thing uses machine learning itself to create a machine learning model for you. This is what you see down here. These are different models that it tries out. And it computes the best possible machine learning model for your task, depending on the point that you choose on your ROC curve here, or on your efficient frontier. It's not an ROC curve. And then what it does is it actually packages everything nicely together and gives you a REST API that you can just query. And suddenly, where you would have hired a data scientist in the past to do this task for you, you can automate this task and do it in like 20 minutes by yourself. And you even get the REST API to use in your startup so that you can deploy the code right away. And that shows that the trend is not really just in the manufacturing or automation space, but it also happens in a space where you have pretty highly skilled workers typically talking about or performing certain tasks. So having said that, let's maybe spend a few minutes to look at the vulnerabilities of these systems. And I think it would be very helpful to understand really what leads to many of these issues, and also to understand a bit better how vulnerable these systems really are in deployment. So my first example is an example of so-called adversarial attacks. So here the idea is that you have an image classifier. What is an image classifier? You show the image classifier an image, and what the image classifier does is it tells you what it sees. Right? I show an image of a panda, and then the classifier says, hey, that's a panda. Okay, and what adversarial training or attack is about is you want to perturb the image in a minimal way. And minimal means that you will not be able to see it with the human eye, or it's actually a very minimal perturbation. And then you run the same perturbed image here through the image classifier. And now the image classifier will tell you this is a gibbon in this case, with very, very high confidence. Okay, so and as you can see, it's very hard to differentiate the two images. In fact, it will be impossible for you to see this. And of course, you might argue now this is all fair and square. That's all in the academic space. It turns out that these are actually very, very real threats that actually impact many of these systems that we would like to deploy in the real world, and especially when we have systems such as autonomous vehicles, where the costs of losses are very high because human life is involved. We should think twice how we deal with these systems. And just to give you a bit of an idea what is actually going on. So first thing that you could say is, well, that's all nice, but I don't have this noise in reality. nobody's going to notice my picture. And that's probably true, but that is, of course, a demonstration only of a general technique. And it turns out, as one of my students did with his colleagues at Google, you can do completely different things. For example, you can compute these, it's called adversarial patches, so these look like coasters. These are disks. And they are computed in a special way, and then you print on it. And then you have an image classifier here, so a VGG16 classifier, which is state-of-the-art image classification. This thing will tell you this is a banana with very high confidence. And now you move this sticker somewhere into the image, so I put it here on the table, and suddenly it believes it's a toaster. Okay? The only thing that you did is you affected a very, very small portion of the input image with this specially computed patch, and it will confuse the system, believing that it sees something completely different. Okay? Now again, you can say, well, that's great, but that is still too academic for me, and maybe nothing of a real-world threat. And in fact, people have shown that you can use the same type of attacks in the real world, and there's the famous, by now famous, stop sign attack. So what you do is you take stop signs and you put these stickers on stop signs. So these are white and black stickers. They have certain sizes and dimensions, and now you have let's play a bit devil's advocate here. You have an autonomous vehicle, and it sees such a stop sign, and now it believes actually the stop sign is not a stop sign, but a speed limit sign. What will happen is it will run over the stop sign, and so on and so forth. And you can imagine that leads to significant issues. And it has been demonstrated that these attacks are pretty robust. So even if you tilt the stop sign a bit or make it a bit smaller, it will still work. So it's not that you need a very specific configuration to make this work. It's actually a pretty robust attack. And very recently, people actually figured out that the vulnerabilities of these networks are actually or that they are much more sensitive than we believe to adversarial inputs. And in fact, it turns out it suffices to change a single pixel in the image, like here, 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 here. I don't see it. Probably here, here, and here, to make the image classifier believe that they see something completely different. And these are state-of-the-art image classifiers. They are trained, these are VGG16 models, so they're state-of-the-art, and it suffices to find a single pixel to make them believe that they see something else. It tells us something about how stable or unstable or robust these technologies are, and it extends to many, many other applications. Now you could say, well, this is all image classification. I don't really care for image classification, but it extends to many, many other domains. For example, image segmentation. So here I have an example. Let's say, again, let's play devil's advocate. Let's think of autonomous vehicles because it's such a nice example. So you have a car, and the car recognizes that there are people in front of the car. So you can, again, minimally change the image. You will be very hard-pressed to say exactly what changed. And suddenly the car believes that this is actually an empty road ahead. And these are all types of issues I think that down the road we should be very aware of, and at least think of how to deal with them before we deploy these things in the real world. Okay, now I talked quite a bit about how vulnerable and sensitive these systems are. So how about humans? So let's maybe look at this picture. So what do you guys see? What animal is this? How many dogs do we have? Awesome, it's actually a cat. So it's the same type of technique. Of course, now you see that there has been a change, right? Because what we did is, I had to change it so that you believe that you see something else. But it's the same type of perturbation, right? So what happens is you perturb the image in a very minimal way, and suddenly you believe that you see something else. All right. Let me close with a couple of takeaways. I think when we use these systems in the real world, there's a couple of things to keep in mind. So the first one, of course, is that you always have to think about fairness and bias in this system, just by the way of how you build them, whether your data set is balanced, and so on and so forth. That's something to keep in mind. And also, I think as academics in particular, we should not just blindly trust these systems and have this idea that just because the results are so amazing that we should just blindly trust the systems, because it leads to all types of problems. So that's on the trust and fairness and bias side. But then, of course, there's all these hacking and adversarial attacks that are very real threats for these systems. So I gave you a couple of examples in the image space. You can do the same thing with text classification, audio classification, and so on and so forth. All these things work exactly the same way. And what is probably very surprising here, so most of these things that I've shown you are typically so-called white box attacks. That means I give you the network, you can essentially get gradient information that you use to maximize the generalization error. But it turns out you don't need that. you can actually use just brute force zero-order black box optimization techniques, and you get very similar results. And that makes it really scary, because it only means that you need sampling access to the system. Put differently, you drive your, whatever, let's say Tesla in the garage, and you can just do, like, I don't know, 10,000 samples a night, and you will be good to go to build your adversarial examples, right? I mean, this is, of course, simplified. It's not that easy, but you just need sample access to the image classifier. It also works for other methodologies. I mean, what I showed you was mostly deep learning based, but we can do the exact same thing for support vector machines or random forest or any other type of classifier. Because what you really do at the end of the day is you force a generalization error of the system. So you just take a black box optimization method and you maximize the loss function and you try to force a generalization error. So it's very easy to do. And also, and I think what that is really the key here, and why why there's a lot of research going on and why people are so concerned, there are really no known methods to prevent these type of attacks. So there's, of course, something that is called adversarial training. So what you do is, while you train the system, you generate these adversarial examples on the fly and you re-inject them into the training process. That works reasonably well, but it also only works up to a certain point. And it somehow only works for the examples that you really have hardened the system again. If I change the attack a bit, you might not be able to have a system that is robust to this or be able to construct one. The other thing is, like, I think the other thing is, even so, people have been thinking about using, say, general noise detectors to detect whether I noised up the image in a certain way. Like you have a test, so to say, before you feed something to the system, and you test whether the input is tainted or not. The problem with this is it has been shown in various experiments that you essentially can work around these safety tests. You can find perturbations. So take these 1 pixel perturbations. This is not noise anymore. It will be very hard for you to detect that. Or you can also change the image in a way that it looks like it's the original image, but maybe you have changed the eye a bit, maybe the eye color, things like this, and it will still lead to adversarial examples. And the other thing is, of course, what you would think, what almost everybody thought in the beginning, ensemble methods will be good enough. So you just train different methods, and you just average together the output, and that is your stable classification of the system. So it turns out that ensemble methods itself are also only of limited help. So even if you mesh together different classifiers or techniques, they will be only robust to these types of attack in a very, very limited way. All right. Yeah, so that's all that I have to say. Thank you very much.
Thank you, Sebastian. We're going to start taking questions from Clayton. Any questions in Clayton? Yes. I don't know who this is. Arisa? All right. And do you have a mic?
Yes, can you hear me? Good. So thanks for the very interesting talk. So I feel that there should be a coevolution between the adversarial attacks and training of the system. Do you have any comment on that? So let me elaborate a bit.
Yeah.
So what I think is that, if we train a system and deploy it, we should be able to come back again and retrain it. If in the stage of building the system, I think about some adversarial attacks and take that into my training, take those adversarial kind of situations in my training, then of course. In future, I may, someone else may come up with some new adversarial attacks to the system. So I should be able to kind of co-evolve the system against, possible new ways of breaking it. So, it seems that, training a system to be robust in any kind of attacks in future seems kind of too much. I'm not sure about your ideas on this.
Yeah, I agree. I mean, a blank slate type of robustness is maybe a bit too much to ask for.
Right.
But I have to say, So I look at the machine learning space in essentially two very separate spaces. So there's what I call the Google and Facebook space, there where you work with digital data, and if you have false positives or false negatives, the cost is pretty low. You don't really care so much, right? It doesn't really matter if you want to classify all the pictures on Instagram and you get a horse for a cat. It doesn't really matter. But it does matter very well when I want to deploy these systems in the real world, because then I need to give performance guarantees and I need a certain form of robustness. And then I would say that the standard to deploy the systems in the real world have to be significantly higher than deploying them in the digital world. And that means that I have to have safeguards in the systems that are also robust, at least to a certain extent, to things that I have not seen beforehand. It's like when you build a skyscraper, your safety factors are so high that even if you haven't seen a wind of a certain force, you still build for that. And I think the same way, if you want to deploy machine learning and AI in the real world, you have to go one step beyond just being able to deal with the current state of the art of problems that you see. I don't know how to do it. I think people are very concerned about this and thinking quite a bit about this because it's very important. And people are very much aware that if you want to build autonomous vehicles and deploy them in the large scale, for example, you need to be able to deal with these situations. But I don't have a solution either.
All right, thanks.
Any more in Clayton? Yes. That's right.
Oh, hello. I agree with Reza that it was a very interesting talk. One question, you were saying that the ensemble methods don't help a lot, but it sounded like you were coming up with a deterministic answer based on the ensemble. How much does randomization help? Because if you're doing adversarial things, it's harder to be adversarial against a random decision.
So I can only talk about the experiments that we have been running, and right now we have been actually focusing on non-deep learning based systems because everybody is looking only at deep learning, but I think there's many other systems that we use that have similar weaknesses. And in this context, we have seen that regularization helps a bit, but not as much as you would like it to help. It's not that it solves the problem.
One more question. Yeah, very interesting talks, thanks. My question would be, is there any general concepts from cybersecurity or from that space that you could use for that? I mean, so my limited understanding of cybersecurity would be that, in former times people always thought, okay, the system is safe until we find a bug, somebody hacks into it, and then we need to fix that. And now they would have all these layers in between, like the memory randomization and penetration testing, that people really try to hack the system and then you fix this. And it seems that some of these things could help solving this problem as well.
Yeah, so people are working very actively on figuring out how to deal with specific attacks. Like for example, for these very easy, for these noise attacks, you could say maybe I just smoothen out the image a bit or things like this. So there are possibilities or tricks to deal with very specific attacks. I'm not sure if they're necessarily motivated by cybersecurity, but the ideas, the paradigms are probably very similar in mindset, in spirit, in terms of what they try to accomplish. I think the problem with this is, again, also in cybersecurity. So I think if you look at cybersecurity, the requirements for a nuclear power plant are very different than the requirements for, your database system. And the reason for this is because the loss in the negative case, in the failure case, is significantly higher. And I think there's a lot of confusion right now, and I don't think that there's really good answers out there at this point. Yeah.
Hi. So my question is, is it possible to sacrifice the performance of the algorithms but make it robust against attacks? Does it work that way?
Yes. So the short answer is yes. It's not a question of whether it is possible. In fact, this happens when you do adversarial training. So typically the performance of the classifier goes down a bit in terms of performance on the clean examples. But what you gain in turn is more robustness on these adversarially formed examples. So it's the way of how it works. So on a mathematical level, what you're doing is essentially robust optimization. So you minimize over the maximum perturbations of your inputs. And that includes, of course, the adversarial one, and then it's a robust optimization problem that you solve. It's highly non-convex. That makes it hard to solve. Otherwise, we would have done this much longer. And the other problem is that the guarantees typically, as always in robust optimization, only hold for the size of the uncertainty set. So if you try to deal with perturbations within an epsilon ball of range 0.3, then as soon as you go beyond 0.3, you will see a very, very sharp increase. And that's what all the papers also show. Up to 0.3, you will be pretty robust. But then at 0.31 already, you will have a significant misclassification rate. So yes, you trade these two off, as in robust optimization.
Okay, more.
Do you think that neural networks are maybe more might be more susceptible to this sort of tampering than others because they're so black box? I mean, with certain other techniques, you can sort of you can make predictions about how the system will behave. You can analyze it. You can understand how it's functioning, and you can sort of spot these bugs beforehand. But with neural networks, you can't so much. Do you think that? Do we know if there's a particular technique that's less resilient?
Yeah, so I think that's a good point. I think that neural networks in particular are very vulnerable to these types of attacks because they are so highly nonlinear. Right? The more you can explain, the more vulnerable you are. Do a linear regression, perturb your inputs, not a lot is going to change. Right? You have something that is extremely robust, but at the same time also not very expressive. And I think the neural networks in particular are vulnerable. But we have seen that also other things like support vector machines and random forests have the same weakness. Maybe not to the same extent, but it's exactly the same things that work.
All right, so perhaps we're going to start with questions here. For those in Clayton who want to ask more questions, Sebastian is going to be in Clayton on Friday, and we'll be giving a seminar, and we'll be also talking to people either before or after the seminar. If you want to talk with Sebastian one-to-one, let me know, and I'll try to schedule this on Friday. So now, coffee questions?
So my take on all of the examples of where things break down, like stop signs or individual pixels, is really that the training data was far, far too small, because if we compare with humans and our visual system, we've been trained on many orders of magnitude more data. And B, that what we're trained on as humans, if I can use that term, is actually video data, and we train in a completely different way. We start from some video of, if we want to learn what a cat is, we'll see lots and lots of projections of that same cat. We start to build up a model of that cat, and then we see some other cats and we build models of what cats look like somehow, rather than individual stills of completely different objects that we've all labeled as cats. So I think the training of these systems is the problem, not the system itself. Sorry, that wasn't a question.
All right, so let me see. So I'm not aware of any work yet that someone has done on video for adversarial training. Given how the general training process works, I would be very surprised if you cannot do something similar. Sure, then you have to modify something consistently across frames. But I think it's only a question of time until this will happen. Because really what you do is, like, from a mathematical perspective, it's not so surprising. You just you maximize the generalization area. You take an example that is in a certain class. Let's say, I don't know what it is, let's say it's a stop sign. And now you just see how you can perturb the input so that you make it switch the class. And so you just search in a ball. And maybe the ball is larger, and it makes it harder to find it, but I think the general technique will work. Now the question is whether it gets to a point where it becomes very obvious what is going on, and then you can have other safeguards. That could be very well. That's the first thing. The second thing is, I do agree with the fact that in general there's much more information in video. There's a lot of people that started now to work on video, and usually you get much better results from video. I don't know to what extent it will resolve this type of issue, but that could be a potential avenue forward. Yeah.
Just a thought to follow up on that a little bit more. Do you think that perhaps some of these issues will be solved just as systems become more complex? So for instance, with the video or image, if you have access to that image or video, you can manipulate it. But say in a real world closed system, if you don't have access to the sensors, like something like a robot, then in order to fool it, you have to, it's more difficult to put noise into the actual real world. So you'd have to construct a whole artificial environment to fool it, perhaps. Or for the example of the stop sign, like there are a lot of other cues, like the context of the scene and the street configuration, all of these things. So it's very difficult to change the whole entire surroundings to fool like a more complex system, perhaps.
That's a very good question. So I have no scientific answer for that. I can speculate. My speculation would be probably along the following lines. It would be probably much harder to do it, but because you build much more trust in the systems, because it happens fewer times, the consequences of this, when you will be successful, will be much more severe. That I think is what will be happening at the end of the day, and that's something that we have seen in risk management, for example. It's the same type of problem. The other thing that I wanted to say about the complexity, so of course nobody's going to noise up the video input. It's way too complicated. But I can print a sticker that literally confuses the system. Now, you might be able to detect that sticker because it's not moving or because it doesn't conform to your scene information that you have. As I said, I have no scientific answer. My speculation would be that you would find the equivalent in that model of adversarial attack. I think at the end of the day it will be like, it will be like a race. Who has the more, I don't know, the more elaborate attack, and then you have the more elaborate defense mechanisms, and it will continue. And I think on a very metaphysical level, humans are not so different, right? Like I can fool you with a lot of things. That's why we go to the magicians. They do nothing else but that, right? And it works. And if you can automate this type of fooling, I mean, the example that I gave in the end with the cat and dog is, of course, a toy example. But I think it shows a very important weakness, also that you as a human, or we as humans, exhibit, right, at the end of the day. And that somebody could exploit. Like, I mean, maybe I can embed something like this into a video, right? And I manipulate you, like how people tried with advertisements 20 years ago, like changing every, 25th frame and show you something different, right? Maybe, I don't know. Yeah.
So should we perhaps just give up in the sense of try, or understand, not give up, but understand the fact that it's always going to fail at some point, regardless of how robust you get and regardless of how much you train it. At some point it's gonna fail, and perhaps try to train for that, and not train. Try to cater for that, to actually figure out when it's going to change, when it's going to fail, what to do then. Because as you said, I think that, as you said, humans also fail. And no matter how complicated and how training and how complex it is, you seem to be always be able to confuse it by making the attack more complex, right? Mm-hmm. And regardless if you put 5 of the AIs together and you assemble them to actually do things that are very clever, I don't think that we can actually build God in infallibility. So, right?
That's a good maybe.
So if it's going to fail, perhaps researchers have been too good at selling it, right? Well, selling the good parts of it.
There's no question about this part for sure.
Yeah. So rather than just selling the good parts, to also sell the limitations, or to not to sell them, but to clarify the limitations, and tell people when it's appropriate to use what, and what to prepare for when it doesn't work.
Yeah, so I think I actually agree. I just want to add a couple of things from my perspective. So I think it's various things. So first of all, I think we need to move away from this alchemy type of paradigm where you just put things together and then when they work, they're good. Just working doesn't mean that they're good. I think that is a big trend. You know, you have these interfaces. You just upload your stuff, you get a classifier, and you think that you did something. Right? That's a bit naive. I think that's the first thing. And in particular, going a step further, I think we should apply more engineering type of principles to the same thing, because we want to build things for the real world. And they are subject to real world constraints, and then they should respect engineering type of requirements that we have proven for many, many years to be the right requirements. That's the first thing. The second thing is I think we need to move away from this black box perspective of the system. Right now I give you a system, and then the system says, I need to cut off your arm, and then you ask, but why? And you say, well, it doesn't matter. I say I need to cut off your arm, right? That's a problem. And so far there has been very little work in making or building systems that explain how they arrived at their conclusion. So as soon as I go to explainability and transparency, this will change a lot, right? Because now, say, let's take my stop sign thing here, right? Like now, you look at the explanation and maybe this thing says, oh, this is actually a 60 mile per hour sign because, I don't know, there's a 60 in there. I have no idea what it would be, right? And then you say, oh, but there's no 60 in there, so you're definitely wrong. So the moment you require explainability, you can also falsify the system, right? It's like, I think the basic principle of science, for example, is that you can falsify a hypothesis. That's the building block. Otherwise, we do like meta-science and alchemy, right? But if I build a black box, I cannot falsify the black box. I give you an answer, and the only way of how you can falsify it is actually with a negative outcome. But you cannot look at the answer and falsify it because I didn't give you any explanation how I arrived at the answer. Now, if I'm required to give you an explanation, this might actually help significantly to like work with these systems in the real world. That's the second thing. And then the third thing, I fully agree. You don't need a system that is perfect. I think it's perfectly fine that you have a system that is, let's say, exceeding human performance. I think that is a good measure. I mean, if it's worse than human performance, you definitely don't want to use it, right? But it should be exceeding human performance or be at par. And then I think it's a valid system to use. And you know, we're all driving cars, and we actually drive with other drivers, and we know that they're not perfect, and we are still driving. So there's always a certain type of risk that you're willing to internalize to participate in the real world. And that will be the same thing here. And at the end of the day, it will probably come down to the question, does it reduce the overall risk of the system? Let's say if I deploy autonomous vehicles and the overall number of traffic fatalities goes down, then I achieve the goal, right? And that's a very measurable goal. And yes, I might suddenly get new types of accidents that I didn't have beforehand because the systems are not perfect. But maybe that trade-off at the end of the day is inevitable, and there's no way of getting around this. Yeah, so I agree. Yeah.
One final question and / remark I want your opinion on. So there's an expression that says error is useful, as in, and for the longest time we didn't have machines around, so that expression was fine. But now, in a sense, people don't expect machines to err, and it's been true for the longest time. When even when we were computer science students, every time we were telling our teachers, oh, the compiler doesn't work, or it says there's a mistake. There's always something that we will find out we did wrong. But even the public also has that impression that the computer is not going to fail. And perhaps people should be educated in the fact that computers will fail. And there's another thing that I would like to add is that if you get hit by a car and there's a driver, you have somebody to blame, and you understand that, well, anyone makes mistakes. I could have made that mistake. I can forgive. If it's a computer, and the person will tell you, well, we've reached this is the optimal algorithm. You've been hit by the optimal algorithm. There's a theoretical bound that we can't go further. This is the best we can do. It's very fatalistic, right? This is you've hit the boundary of how nice things can be. And so I think I have a problem with that, and I think many people have a problem with that.
Okay, so I'm just commenting on this. Again, for many of these things I have no opinion because it's very hard to have a good opinion on this. There's so many complexities to keep in mind. So I think the first one is, so I don't know, the Pope made a statement about AI about a year ago to reconcile AI and humans. And he had a very nice answer to AI's human thing. He said, well, it's all built by humans, so of course it's subject to the same rules. Okay, that was his answer to that question. I'm just giving you the same answer. And the other thing is, I think the fundamental differences between a computer and a human is that if I take 100 humans, they all make different mistakes. And on average, I have a pretty good system. But if I will build one computer system, it will systematically make the same type of mistake. And I think that is an issue. So if you build, and that's why people don't like it. It will have a bias in a specific direction. If you now build 100 different systems with 100 different setups and all these biases average out, then it will be probably also fine. But if you, let's say, deploy an autonomous vehicle fleet with 500,000 vehicles, they all run on the same code and they all, kill all people with like orange jackets, for example, right? That is a problem, right? Because you have a systematic bias in the system. And I think that is the difference between why you're willing to treat the failure of a human person different than from a computer system in general. Because a human, you say, well, this one made this mistake, this one, and then you say, oh, we are all different, and we are all like a big zoo. Right? That's typically how the argumentation goes, and it's fine. But that's not true for computers anymore, because you program them with the same code. They're not from a different zoo. They're all from the same kind. It's copies of the same thing, and I think that makes a big difference. Yeah.
Thank you. Let's thank Sebastian again.